And the interesting thing is that you can see that the main equation holds for phi in the following nice way. So take this length here and convince yourself that this length is the same as this length. That's the next smaller pentagram there. This length plus this length, which is the next smaller one. They alternate blue and green. So why is this big line as long as this line plus this line? See, that fact is the same as the fact that 1 plus phi is phi squared. Each time these lines are getting bigger by the same factor. But it's not just that each one is getting bigger by the same factor. It's that each, as you go along, the small one plus the next bigger one is equal to the length of the next biggest one. Well, it's actually really easy to see why that's true, because here's why. So if we take this long one here, we can chop it right here. And then this long part of it is just as long as this one here. And then the rest, this part here, is just as, if you just draw a parallelogram, if you just go up here, you see it's just as long as this one. So if you stare at it for a while, you can see it's just obvious that all these pentagrams are, as you climb up to the tips and get smaller, they're all getting smaller and smaller by a constant ratio. But that ratio has the property that 1 plus phi is phi squared, because I'm saying that 1 plus phi is phi squared. And in fact, the fact that this thing never stops, the fact that it keeps on going on and on and on forever, you can see, if you scratch your head a bit longer, that that's the same fact as the fact that the continued fraction expansion of phi never ends. So that if you were a smart Pythagorean, you could just stare at this thing for a few weeks or months or years, and you'd conclude that the golden ratio, so-called golden ratio, had to be an irrational number. And what do you get for it? They throw you off a boat and drown you. So that's what we get. So in fact, it's not just true of the golden ratio that the continued fraction expansion never ends. For any irrational number, it never ends. And for any irrational square root, it repeats in a very nice way. It gets stuck in a loop. It starts repeating. So for the square root of 2, that turns out to equal 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2. Square root of 3 is 1 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 2. So this one goes, after a little while, it starts going 1, 2, 1, 2. So they all these irrational square roots, they have sort of cute continued fraction expansions. But what's special about the golden ratio is that it's the simplest one of the lot. The golden ratio is the very simplest one. It just has all ones. So you wouldn't have necessarily expected that the very simplest one of all these guys would be the square root of 5 plus 1 over 2. But that's true, and that's what's sort of special about the number 5, really. That's what the 5-ness of the pentagon is making, and the pentagram is making the golden ratio be the very simplest of all the continued fraction expansions. And there's a certain way in which it's the most irrational number, meaning that it's very hard to approximate the golden ratio very well by nice, simple, rational numbers. Let me show you why that's true. So the way you get a really good approximation of a number by a fraction, by a rational number, is to take its continued fraction expansion and then just quit at some point and then figure out what fraction you've got. And this way of getting a good approximation, it works really well when you quit right after you hit a really big number. So it's easiest to explain by an example. So this is the continued fraction expansion for the number pi. So you know pi is like 3.14159, blah, blah, blah. But you can also write it out as a continued fraction expansion. You can work it out, and it's 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus 1 over 292 plus 1 over something and something. And this one doesn't satisfy any pattern. No one knows what the pattern is. It's just some crazy bunch of numbers. But 292 is, of course, nice and big, so it might be fun to stop then. In other words, say, OK, I quit. I'm just going to stop there. And I won't get exactly pi if I stop there, but I'll get some number that's hopefully pretty close to pi. So let's do that. Well, actually, you could quit way before then. You could say, I'm going to quit as soon as I get to 7. 7's pretty big, so I'll just stop there. So I'll say pi is about 3 plus 1 over 7. Well, that gives you an approximation to pi that people talk about a whole lot. At least they used to before calculators were invented or something. So 22 over 7 is a sort of famous, pretty decent approximation to pi. It's 3.1428, which isn't too bad. It's got 2 decimals right. But if you wanted to do a lot better, you could say, I'll work a bit harder. I'll go down to this 292 here, and I'll quit then. So I'll take this big thing here, and I'll work out what it is. You just grind away. You work it out. It's 355 over 113, which is sort of cute, right? Because it's like 1, 1, 3, 3, 5, 5. That's just a coincidence. It doesn't mean anything. But anyway, what the heck, you know, take advantage of it. So, but the neat thing is that that's an incredibly good approximation to pi. It's 3.1415929, blah, blah, blah. And pi is 3.1415926, blah, blah, blah. So it gets the first 6 decimals right. And interestingly, it was discovered in 480 AD by a Chinese mathematician, Zhu Shangqi. So clearly, some people had lots of time on their hands back then. Now, if you take the golden ratio and you try to do the same kind of thing, you're never going to hit a big number in the continued fraction expansion. It's just all ones. So it works very slowly and pathetically. So the first approximation gives you 2 over 1, which is 2. The next one gives you work it out, you get 3 over 2, then 5 over 3, 8 over 5. So these numbers here, they're wiggling up and down. 2 is big, 1.5 is small, this is big, that's small. They're wiggling up and down, getting closer and closer to the golden ratio, which is 1.6180339, blah, blah, blah. But they're going very slowly, and to actually get 6 decimal places right, you'd have to go a lot further out than you do for pi. You'd have to go to 1597 over 987. So that's what I mean by saying that the golden ratio is the most irrational number. You can actually be more precise than I want to be right now and say and prove that the golden ratio is sort of the hardest number to find good approximations of by fractions. These fractions are actually famous. If you've ever studied some numbers called the Fibonacci numbers, that's what's showing up here. But that's a whole other story, and I don't think I want to talk about Fibonacci and his rabbits and all that stuff. Instead, what I want to say is what's so great about the fact that the golden ratio is the most irrational number. The point is that nature likes rational numbers. For example, if you have a nice chord like an octave, it's because 2 people are singing or 2 piano strings are vibrating at 2 different frequencies. One is wiggling just twice as fast as the other. So an octave just means one thing is wiggling twice as fast as the other. Or a fifth, which is another really nice sounding chord. Da 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 da. You just go up 5. I probably went up 6 because I can't count. But if you go up 5 up the scale, turns out that the high-pitched one is just 1.5 times, it's wiggling 1.5 times as fast as the slower one, 3 halves.